Assalamualaikum and good day everyone. Today we'll be presenting our group assignment for the subject Control Principle. Our project is titled Control Principle System Design Analysis. I'm Afif Rafiq together with Muhammad RAZIQ and Cik HISHAM from BERE2364 S2/1 Data Entry. Let's begin with short introduction. Control systems are critical in engineering fields like automation, robotic, aerospace, and power systems. Their main role is to make sure that output remains predictable even when there are changes or disturbances. In this project, we explore how theory connects with practical applications using a second-order dynamic systems. The objectives of this project are as follows. First, to derive and analyze the system transfer function. 2. To convert it into a state space form. 3. To analyze how the system responds. 4. To design a controller that improves system performance. And 5. Finally, to validate our design and analysis using MATLAB simulations. A little bit about our background study. MATLAB is our main tool for this project. It helps us simulate models, generate step responses, create board plots, and analyze post-zero behavior. Control systems help regulate output based on changing inputs are key to maintaining system stability and performance. Two major modeling approaches are used. First is transfer function, which works in the frequency domain, and state space representation, which operates in the time domain. For second order systems, performance is influenced by three parameters: natural frequency, omega n, damping ratio, zeta, and system gains, k. We move on to part A, which is system modeling. The modeling was done in two domains, which is frequency domain and state space representation. We'll first look at the transfer function approach. In the frequency domain, we derive the system's transfer function using Laplace transformation, assuming zero initial conditions. MATLAB was used in simulations. We use the step function for the unit step response and pole and zero functions to identify the system dynamics. From the analysis, we found no zeros and two complex conjugate poles at negative 0.25 plus minus 0.33i imaginary. These complex poles indicate that the system is underdamped, which we'll explore further when we analyze the response. Next is the state space model. This response describes the system through first order differential equations. It captures internal state behavior better than transfer functions. The model was derived from the transfer function into the generated state space form using MATLAB. We compare the two models. Transfer functions are simple and good for input-output behavior and stability analysis. Meanwhile, state space is better for analyzing internal behavior and is more suitable for complex systems. The performance from both models was then compared. Theoretically, the rise time are 4.83 seconds, peak time are 7.26 seconds, settling time are 16 seconds, and overshoot are 16.4%. Meanwhile, for the MATLAB, we got the rise time, which is 4.8 seconds, peak time are 7.3 seconds, settling time are 16 seconds, and overshoot are 16.3%. In conclusion, MATLAB simulation gave similar results with minimal deviation. This confirms the accuracy of our models and its validity. Thank you.
So, Assalamualaikum and good morning to the doctor and my friend. So, I continue the presentation to part B, controller design. So, what is controller design? Controller design involves modifying system behavior using a gain compensator to achieve specific transient response target. So, design criteria first. Design criteria: target overshoot 5% until 25%. So I choose the overshoot target which is 10% overshoot. The method adjust gain k, which is I calculate until I find the k using the open loop transform function to shift closed loop pole. So the system configuration open loop transfer function that I get gs equal to 5k divide open bracket s plus 10, close bracket, open bracket, 4s power 2 plus 2s plus 1, close bracket. So I get the k equal to 2.15. So the tool that I use to simulate is which is MATLAB function, which is step info, board and margin. Simulate state response and frequency characteristic to tune controller. So this is a simulation result. On my left, the output graph simulation MATLAB that I assume k equal to 1. So I get the open loop gain and phase margin. Firstly, I calculate to get the frequency first. So as you see this, I get the 99.3 degree, which is the frequency 0.529. So I align with the magnitude graph. I align 0.527. So I get the magnitude 6.64. Then I change the dB to, so I get the k value, which is 2.15. So I change the code in MATLAB, which is k is 2.15. So I get the gain margin 25.8 dB at 2.29 radian per second. So the first phase margin that I get 79.8 degree at 0.533 radian per second. And for additional, I find the step response for closed loop, which is this is simulation. Continue. So performance analysis, that command window simulation MATLAB, which is as you can see, I calculate the rise time, settling time, overshoot and steady state for the open loop and the closed loop. So MATLAB simulation was used to evaluate the closed system after applying the gain compensator. The key performance metric analyze rise time, peak time, settling time, and the percent of overshoot. Percent overshoot was within the acceptable range of 50% to 25%, indicating proper gain tuning, which is K. Both rise time and peak time were reduced, showing improved system responsiveness. Settling time TS improved slightly, meaning the system stabilized faster with fewer oscillation. The system remains stable, confirmed by pole located in the left half of the S-plane. Transient response was smooth with no associated oscillation or delays. The system achieved a strong balance between speed and damping. Overall, the controller design improved performance while maintaining the stability and control. So that's all for me for part B, controller design. Thank you. So I will pass the next presenter for part C.
Assalamualaikum and a very good morning to our student and Puan Sharatun. So before we start, my name is Muhammad Raziq bin MAZLAN. My matrix number B122 410 630. So for today, I would like to introduce part C. It will about stability analysis. So for verify the stability of our closed loop system, we use the classical Horowitz criterion. This method involves constructing a rough array, which is done step by step, row by row, using only the system characteristic equation. So for each row in the row array is derived from the previous two rows. The main objective is to check whether on any roots of the characteristic equation lie in the right half of the complex plane. If all the roots or pools are in the left half, the system is considered stable. So, why rough Hurwitz? Rough Hurwitz is particularly useful because it allows us to analytically verify stability without relying on complex graphical or numerical technique. This is especially valuable after control design to ensure that gain adjustment haven't destabilized the system. So, for MATLAB analysis, we support our theoretical analysis with MATLAB using the PZMAP function. We identify the post location, one real pole at minus 10.03 and a pair of complex conjugate poles at minus 0.236 plus minus 0.679 I. All poles are located in the left half of the S-plane, confirming the stability of the system. So for the discussion, this stability analysis reinforces the reliability of our controller design. The Roth-Hurwitz criterion provide a clear analytical method, while MATLAB's visualization tool help confirm our finding. So for overall, the system is stable and the position suggests a well-damped control response. This step is essential to ensure that our system doesn't just respond quickly but also remain predictable and safe under dynamic conditions.
So I will continue the part of the conclusion of the assignment project control principle. So the result, the assignment we successfully model a second order system and design a controller to meet specific performance criteria. So the key accomplishment, we derive system equation in both transfer function and space form. Secondly, we verify the model accuracy using theoretical and simulation data. 3. We also design a gain compensator to improve transient performance. Number 4, we also validate stability with classical analysis and MATLAB visualization. So the final outcome, overall, we have achieved an overshoot within the acceptable range, which improve rise and settling time, and also establish a strong foundation in control principle applicable to more advanced and control system. Okay, that's all from our group. Thank you.